Welcome back to the deep dive. Today, we're pulling back the curtain on something really fundamental in tech, machine learning classification.
Yeah, it sounds technical, but it's actually happening all around us.
Totally. Think about your email sorting spam or, your phone recognizing your face. That's classification doing its job quietly in the background. It's kind of the core of a lot of AI smarts.
Exactly. And understanding it, well, it gives you a shortcut to seeing how so much of our digital world actually makes decisions, how it organizes all that information.
So our mission today is basically to unpack how computers learn to sort things. It really just comes down to putting items into the right boxes,
hmm
like sorting your laundry, right? You've got a clean pile, a dirty pile, simple.
That's the basic idea. But scale that up to millions of emails or images or complex data points.
And suddenly it's incredibly powerful.
Right. And hopefully by the end of this, you'll really get a feel for the techniques and maybe some of the challenges behind that so-called magic.
Okay, let's start with the big one. Supervised learning. We hear that term a lot.
We do.
Yeah.
And at its heart, it's like teaching a computer with a really detailed answer key.
So you give it examples.
Exactly. You show it an input, like an email saying, win a free iPhone.
Uh-huh. Obvious spam.
Right. And you explicitly tell the computer, that's spam. That's the label. It learns the connection between the input and the correct answer.
So it's learning with a teacher, essentially.
Precisely. And the really cool part is, after seeing enough labeled examples, it starts to figure out the patterns. Then it can look at a new email it's never seen before.
And make a pretty good guess whether it's spam or not.
Exactly. It generalizes from what it was taught.
And these boxes or categories we're sorting into, those are the classes, right?
Yep. Classes are just those predefined categories, spam or not spam.
Or like in a health app, maybe healthy or sick.
Perfect example. Or for photos, it could be dog, cat, bird. Each item gets assigned to one specific class.
Okay, makes sense. But just like there are different ways to sort laundry, maybe. There are different kinds of classification.
You got it. Different flavors, you could say. The simplest is binary classification.
Binary, so?
Two options.
Just two. Yes or no. Spam or not spam? Will the customer click or not click? Simple, direct choice.
Okay. What if there are more than two options?
Then you're likely looking at multi-class classification. Think more than two categories, and this is key, only one answer is correct for any given item.
Oh, like a weather forecast. It can be sunny, rainy, or cloudy, but it can't really be all three at the exact same moment.
Precisely. Only one label applies.
But sometimes
Yeah.
multiple labels can apply, right?
Absolutely. And that's where multi-label classification comes in. Imagine you're tagging photos, a picture of a beach at sunset.
Okay, yeah, it's definitely a beach.
And it's also definitely a sunset.
So you'd want both tags.
Right. Multi-label lets you assign multiple relevant categories simultaneously.
Interesting. Now, you mentioned challenges earlier. What about when the data itself is skewed? Ah, yes. Imbalanced classification. This is a really important one in the real world. It's when one class is way, way more common than the other.
Like finding a needle in a haystack?
Sort of. Think about detecting credit card fraud. Most transactions, thousands of them, are perfectly normal, legitimate.
Right. Only a tiny fraction are actually fraudulent.
Exactly. Maybe 1 in 1,000 or even less. And the danger here is that a lazy model could just predict not fraud for everything.
And it would be right 99.9% of the time. Sounds great, but
But it would miss every single fraudulent transaction, which is the whole point.
Yeah.
The standard accuracy just doesn't cut it here. You need smarter ways to measure success.
okay, that makes sense. So how do computers actually do the sorting? What are the methods, the algorithms?
Right. The algorithms are the different strategies the computer uses. There are quite a few, each with its own strengths and weaknesses.
Let's maybe start with one that sounds a bit misleading, logistic regression.
Yeah, the name throws people off. It's not really about logistics, and it's used for classification, not regression in the usual sense.
So what does it do?
At its core, it calculates a probability. The probability that an item belongs to a particular class, usually if that probability is over a threshold, like 50%.
It predicts, yes, that's the class.
Exactly. So maybe it calculates an 80% chance a customer will buy something based on their data.
Yeah.
The model says, yes, likely buyer. Below 50%, it says no.
And you mentioned it's interpretable.
Often, yes.
Yeah.
You can usually get a sense of which factors push the probability up or down.
Okay, what's next?
How about K-nearest neighbors, or KNN? This one's quite intuitive.
K nearest neighbors. So it looks at things nearby.
Pretty much. To classify a new data point, it just looks at the k closest data points it already knows about in the dataset.
K being just a number you choose, like the 3 closest or 5 closest.
Exactly. You pick k, then it sees what class the majority of those neighbors belong to.
Like if you walk into a section of a crowd and everyone around you is wearing, say, a red hat.
You probably guessed the next person to join that little group is also wearing a red hat. The new point gets classified based on its neighbor's majority vote. Simple, but can be effective.
Cool. Okay, what about support vector machines? SVMs. Sounds more complex.
They can be, but the basic idea is quite visual. Imagine you have two groups of data points, like apples and oranges, scattered on a table.
Okay.
An SVM tries to find the best possible straight line, or in higher dimensions, a hyperplane, to separate the apples from the oranges.
Like drawing a line between them. But what's the best line?
It's the line that creates the widest possible margin, the biggest empty space, between the line itself and the closest apple and the closest orange. Maximize that gap.
Okay, maximizing the separation. But what if you can't separate them with a straight line? What if they're all mixed up?
Great question. That's where SVMs get clever. They use a trick called the kernel. Yeah, it's a mathematical function that essentially warps the data, pushes it into a higher dimension where hopefully a straight line can separate the classes. It finds complex boundaries without explicitly calculating those higher dimensions.
Sure.
Pretty smart.
Wow, okay. That's clever. What about decision trees? You mentioned those earlier, sounding like a flow chart.
Exactly like a flowchart, or like playing a game of 20 questions.
Oh, so?
The algorithm learns a series of questions to ask about the data. Simple yes-no questions like, is the person's age greater than 30?
Okay.
Yes. Okay, next question. Do they own a home? No. And so on. Each question splits the data further down the tree.
Until you get to a leaf node that tells you the class, like likely to buy or unlikely to buy.
Precisely. Based on the path taken through the questions, they're very easy to understand and visualize. You can literally see the decision path.
But maybe one tree isn't always enough. I feel like I've heard of random forests.
You have. Random forests built directly on decision trees, instead of relying on just one tree.
You use a whole forest of them.
Exactly. It creates many different decision trees, each trained on slightly different data or considering different features.
And then, how do they decide?
Each tree in the forest gets a vote on the classification for a new data point. The final prediction is simply the class that gets the most votes.
Like getting multiple opinions.
Right, like asking, say, 10 different doctors for their diagnosis. If 8 out of 10 agree you're healthy.
You feel a lot more confident than if you just asked one.
Exactly. It makes the overall prediction much more robust and usually more accurate than a single tree. Less prone to errors from one weird tree.
Makes sense. Okay, one more algorithm you mentioned, naive Bayes.
Naive Bayes. This one uses probability theory, specifically Bayes' theorem. It calculates the probability of an item belonging to a class, given the features it has.
Okay, probability again. But why naive?
It's called naive because it makes a big simplifying assumption. It assumes that all the features are completely independent of each other.
Which probably isn't true in real life, right? Like, if an email has the word free, maybe it's also more likely to have the word prize. They aren't independent.
Exactly. That independence assumption is almost always technically wrong. But, and this is the interesting part, even with that naive assumption, the algorithm is often surprisingly effective, especially for text classification.
Like spam filtering.
Yep. Guessing if an email is spam by looking at the probabilities associated with words like Viagra or lottery, even assuming those words appear independently. It's fast, simple, and often works really well.
Huh. So sometimes being a bit naive actually works out.
In this case, often yes. Computationally cheap and effective.
Okay, so we have all these ways computers can learn to sort things, but
Yeah.
how do we know if they're actually any good at it? How do we test them?
Evaluation. Crucial step. It's like giving that student an exam after they've done the learning.
But maybe more complicated than just a percentage score.
Well, the simplest metric is accuracy. That's just the overall percentage. How many did it get right out of the total? 90 correct out of 100 predictions is 90% accuracy.
But we already said that can be misleading, especially with that fraud example.
Exactly. Accuracy can hide serious problems. That's why we need to dig deeper, usually with something called the confusion matrix.
Confusion matrix. Sounds confusing.
A little. But it's just a table. It breaks down the predictions into 4 categories. It shows you not just how many were right or wrong,
Right?
but how they were right or wrong.
Okay, what are the categories?
You have true positives, TP, it correctly predicted yes. True negatives, TN, correctly predicted no. False positives, FP, it predicted yes, but it was actually no. And false negatives, FN, it predicted no, but it was actually yes.
Ah, okay. Let's use an example. Maybe a medical test, like for COVID.
Perfect. A true positive. Test is positive, you have COVID. Yeah. True negative. Test is negative, you don't have COVID. Both good.
Right. False positive?
Test says positive, but you don't actually have it. That's maybe annoying. You might isolate unnecessarily.
Okay. And the false negative?
Test says negative,
Mm.
but you do have COVID. That's the really dangerous one, right? You might go out and spread it.
Yeah, okay, so the confusion matrix shows you exactly how many of each type of error occurred. Not all errors are equal.
Precisely. It gives you that crucial context. And from the matrix, we can calculate other important metrics, like precision.
Precision? What does that measure?
Precision asks, of all the times the model predicted yes or positive, how many times was it actually correct?
So, back to the police analogy from earlier. If my officers made 10 arrests predicted guilty, how many of those people were actually guilty?
Exactly. It measures the reliability of the positive predictions. High precision means when it says yes, it's likely correct.
Okay. And then there's recall.
Right. Recall asks a different question. Of all the things that were actually yes in reality, how many did the model successfully find or catch?
So, sticking with the police. Of all the people who were actually guilty out there, how many did my officers successfully arrest?
Perfect analogy. Recall measures how completely the model finds the positive cases. High recall means it finds most of the actual positives.
And these can be trade-offs, right? You might become really precise by only arresting people you're absolutely sure about, but you might miss a lot. Low recall.
Exactly. Often improving one hurts the other, which is why sometimes people use the F1 score.
F1 score.
Yeah, it's simply a way to combine precision and recall into a single number. It's the harmonic mean of the two. Useful when you care about both types of errors.
Got it. A balanced measure. And one last term, loss function. You mentioned that briefly.
Yes. The loss function is used during the training process. Think of it as a measure of how wrong the model's predictions are compared to the true labels in the training data.
So it's like the penalty for making a mistake while learning?
Pretty much. The entire goal of the training process is for the algorithm to adjust its internal settings to minimize this loss, to make fewer and smaller errors over time. It guides the learning.
Okay. So algorithms learn. We evaluate them carefully. Where does this leave us? Where do we see classification in action?
Honestly, almost everywhere in the digital sphere once you know what to look for.
We mentioned spam filters. That's a big one. Keeps our inboxes usable.
Definitely. But also things like medical diagnosis assistance, looking at scans or symptoms.
Analyzing customer reviews.
Yeah.
Figuring out if they're positive or negative.
Yep. Sentiment analysis, that's classification. Face recognition on your phone or tagging friends in photos.
Classification again.
Recommender systems suggesting movies or products based on categories you might like. Even systems that check if a car ran a red light from camera footage.
Wow, it really is underpinning a lot.
It truly is. Understanding these concepts, even at a high level, really demystifies a huge chunk of modern technology. It moves you from just using these tools.
To actually having a sense of how they work, how they make decisions that affect you.
Exactly. It's empowering knowledge.
So we've gone from simple sorting, like laundry, through all these different algorithms. Logistic regression, KNN, SVMs, trees, forests, naive bayes, and how we check if they're doing a good job with things like precision, recall, and that confusion matrix.
It's quite a journey, but the core ideas are accessible. And knowing them really changes how you see the world around you, especially the digital parts.
Absolutely. So maybe the next time you see an email land perfectly in your spam folder, take a second. Remember, there's a pretty sophisticated classification model behind that decision.
One that used labeled data and algorithm, maybe balanced precision and recall.
And now you have a real insight into how it probably works, and maybe even where it could sometimes get confused. Think about what other classifications are happening around you, making decisions for you, and how this understanding might change how you interact with it all.